Hello, ME312. We are Team 7, and we are here to present our final project. So without further ado, let's go into the introduction here.
Our goal for this project is to design a robotic arm that meets these requirements. A zero steady state error has an overshoot of under 10%. A steady state error of 0 has an overshoot of under 10%, and a settling time that is less than 1 second. Our system schematics are given here as 1 kilogram of mass, acceleration of gravity, an arm length of 1 meter, and a dampening ratio of 7.
You can see for our method approach, we used a PID. PID control is a proportional integral derivative controller, and the function of the controller is, as you can see, is written below. But further in our PowerPoint, you can see the equation expand more. And for our analysis, we're going to use PID control because it gives us a very high degree of control over the system. And benefits of using PID control are that it will improve transient response time along with our two customer requirements, and integral controller used in project 2 will eliminate steady state error and minimize the overshoot under 10%, and PID will meet all PID will satisfy all the requirements. And the biggest problem with our project 2 using iSystem in the previous project was we couldn't meet 1 second of settling time. And so our main purpose was to meet all three, and including the 1 second. So the proportional derivative controller is the PID controller was used to speed up the settling time, and paired with the I controller, we were able to meet all of our design requirements. And as you can see, this is our assumptions for EOM, and this is our general form of EOM. And here's our block diagram and time response, and the full system model is to the left, and that's basically our plant dynamics. And as you can see, our equation over here. So basically we did a simple math and divided by 0.38 to get into a simpler form of equation like that. And we rewrote it to show the pulse. And as you can see on the bottom, here's our pulse also. A step input is applied to the system. This is allow us to view our transit and steady state response. And the design will broke down into two pieces actually. Finding a zero based on open loop pull to improve transient response using angle and magnitude quotation and PD response A, and finding a zero to reduce steady state error from PI response B.
Yeah, and I'll take over from here and explain more about the controller design itself. So as mentioned earlier, we were going to use the angle and magnitude criterions to solve this. So in our plot here, we have our open loop poles as discussed previously. Our desired pole can be found from this equation here. We've found those constants a few times before. So we do that, we end up with our desired poles at -40 and plus or minus 42i. Using this diagram, we can then find the angles θ1, θ2, θ3, and then set all of those equal to -180 degrees, solving for θ3 and getting an angle of 75.151 degrees. Then to find the constant A, which would actually appear inside of the PD portion of the controller itself, we can solve this equation here, and that will give us the result 50.85 as seen in the PD control here. And then finally, we can use the magnitude criterion to determine a sufficient gain for the system, which we found to be 6.69. You might also notice from above that we over-engineered the system response. This was in an attempt to, on the first design iteration, to hit all of the goals, since these hand methods, while they are good as approximations, sometimes don't hit the goals when you put in the original requirements. And after we do that, we evaluate these using MATLAB. So we're able to evaluate our step response. So the initial diagram is shown on the left here. You can notice that the biggest issue with it is that the settling time is far too long. It takes a very long time to get to the settling time of the actual, to get the system to settle. So what we do is we use MATLAB as a tuning tool. And then by increasing the gain, we can actually end up with a system that meets all requirements. You can see here that the settling time was 0.05 seconds. Our overshoot was 9.39%. And on the right-hand side here, we have the two graphs, which we will cover in a little more detail just after this. So for the transient results, we have our system model here. We saw this earlier as Janik showed us. That was the plant model. This captured the physics of the robotic arm. When we put the controller in series after the design iteration, we end up with this enormous equation here. And then we can just run that simulation through MATLAB. That gives us the response on the left here, confirming the results of what our overshoot percentage and settling time was before. And from previous knowledge that we've gained, we can also see that G of S up here is a type 1 system. And for a step input, any type 1 system will have 0 steady state error. So this will meet all of the requirements that the customer gives us. We also take a look at the frequency response of the system as well. We can see on the left here that there is a Bode diagram and a result for the bandwidth of the system, which came from simulations that were done in MATLAB. We can see from the result on the left that the system is very stable and that the high bandwidth implies a capability to handle very aggressive inputs as well, meaning that the system has a wide range on which it can operate. And as mentioned earlier, the controller meets all requirements and is a successful design. This is shown by both plots and the results from our simulations.
So overall, using the general form function of a controller given right here, we were able to design a proportional derivative controller to control the settling time and the overshoot percentage, meeting our customer requirements, which were given right here. Based on the customer's expectations, we were able to meet expectations and come up with a PD controller and a PI compensator, given the equations right here. And for future work, further refinement could be conducted to improve the PID controller and overall transient response based on the customer feedback from the initial system.
Yeah, and you can see the logistics of all the work here. And we would like to thank you for listening to our presentation today. We'd be happy to answer any questions you have. Thank you.